Take, for instance, tardigrades, also known as water bears. These tiny, nearly indestructible creatures can endure the vacuum and radiation of outer space, extreme temperatures and high pressures. Their resilience suggests that life, if it exists elsewhere, might not be confined to Earth-like conditions. Another remarkable example is the discovery of microbial life miles beneath Earth's surface in rock formations, illuminating the possibility that life could persist in similar subsurface environments on other planets or moons. The study of extremophiles thus informs the search for life on other planets and moons. The icy moons Europa and Enceladus, which have subsurface oceans beneath their frozen crusts, are prime candidates for harboring life. The presence of hydrothermal vents on these ocean floors could provide the necessary heat and minerals, much like the vents on Earth where extremophiles thrive. Mars, with its evidence of past liquid water and present subsurface ice, is another focal point, especially in regions with perchlorates where halophiles might potentially survive. By studying extremophiles, scientists can better design missions and instruments to detect life in extreme conditions beyond Earth. For instance, NASA's Perseverance rover on Mars aims to collect samples that may contain signs of ancient microbial life, searching in places analogous to Earth's hydrothermal environments. Instruments are designed to detect specific biosignatures, informed by what we know about extremophiles. Extremophiles serve as Earth's gritty ambassadors in the quest to understand life's potential beyond our planet. They demonstrate that life can adapt to a myriad of extreme conditions, broadening the horizons for astrobiology and offering valuable insights into where and how we might find signs of life elsewhere in the cosmos. Detecting life on other planets involves identifying key indicators or biosignatures that strongly suggest biological activity. The primary focus is on finding chemical, physical, and sometimes even geological markers that either directly or indirectly point to the presence of life. These indicators vary from the atmospheric composition of a planet to surface features detectable through telescopes and space missions. One of the most crucial biosignatures is the presence of specific gases in a planet's atmosphere that are often associated with biological processes. Oxygen, for example, is a strong indicator because it is highly reactive and depletes rapidly without continuous replenishment. On Earth, this comes from photosynthesis. Methane is another significant gas since it can be produced by microbial life. When found together, oxygen and methane could be particularly telling because they react with each other, mutually depleting their concentrations unless replenished by some processes, suggesting a dynamic balance likely maintained by life. Another key indicator is the presence of liquid water. As a universal solvent, water facilitates most known biochemical reactions. Many mission designs, like those involving Mars rovers or Europa landers, focus on finding signs of liquid water or its past presence. Features such as river valleys, lake beds, or the spectral signatures of hydrated minerals hint at the history of water and its potential to harbor life. Surface features and geological formations also play a critical role. For instance, stromatolites, layered structures created by microbial communities on Earth, provide direct evidence of microbial life. Finding analogous structures on other planets or moons might suggest similar life forms. Additionally, fluctuations in the reflection spectrum of a planet's surface, indicating vegetation or other biological activity, are scrutinized by telescopic observations. Organic molecules, complex carbon-based compounds, are another promising indicator. Missions like the Mars Curiosity rover have found tantalizing hints of complex organic molecules in Martian soil. While not definitive proof, the presence of these compounds can point to prebiotic chemistry or even active biological processes. Technosignatures, or signs of advanced technological civilizations, represent another fascinating aspect. These could include unusual patterns of light that might indicate artificial structures or waste heat detected through infrared telescopes, suggesting large-scale energy use. Radio signals or other forms of communication could also be indicators, which initiatives like SETI, Search for Extraterrestrial Intelligence, aim to detect. Key indicators of life on other planets span a range of evidence, from specific atmospheric gases and liquid water to geological formations and organic molecules. Each of these clues helps build a compelling case for the potential presence of life, guiding the design and focus of space missions as humanity continues the quest to discover whether we are alone in the universe. The search for biosignatures on exoplanets is a multifaceted endeavor that relies on advanced technology, intricate methodologies, and a deep understanding of both astrophysics and biology. The primary tools for this quest are powerful telescopes, both ground-based and space-based, equipped with sophisticated instruments capable of analyzing the light from distant celestial objects. Through a combination of techniques like spectroscopy, direct imaging, and transit observations, scientists aim to detect signs that might indicate the presence of life. Spectroscopy is among the most crucial techniques used in this search. When a planet passes in front of its host star, starlight filters through the planet's atmosphere, and molecules in the atmosphere absorb specific wavelengths of light. By examining the resulting spectrum, scientists can identify the chemical composition of the atmosphere. For example, the James Webb Space Telescope, JWST, uses infrared spectroscopy to analyze the atmospheres of exoplanets, looking for key gases like oxygen, methane, and water vapor, which could signal biological activity. Direct imaging, although challenging due to the vast distances and the brightness of host stars, is another method gaining traction. Coronagraphs and star shades are technological innovations that help block the star's light, enabling telescopes to capture reflected light from the planet itself. The spectra obtained from this reflected light can provide detailed information about the planet's atmosphere, surface conditions, and potential biosignatures. Future missions like the proposed Large UV/Optical/IR Surveyor, LUVOIR, aim to employ these technologies to directly image Earth-like exoplanets and their potential signs of life. Transit observations offer yet another avenue. When a planet transits its star, it causes a slight dimming of the star's light. Analyzing these light curves helps determine the planet's size, orbit, and even hints of atmospheric conditions. Space telescopes like TESS, Transiting Exoplanet Survey Satellite, and its predecessor Kepler, have been instrumental in discovering thousands of exoplanets by this method. Moreover, by examining how the starlight changes during the transit, scientists can deduce the atmospheric composition. Ground-based telescopes also play a vital role in this hunt. Instruments like the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, will possess the resolution and light-gathering capability to find and analyze exoplanetary atmospheres. These observatories, despite the challenges posed by Earth's atmosphere, offer higher resolution and the ability to conduct long-term observations. Combining these methodologies provides a multidimensional picture of exoplanets and their potential for harboring life. The ultimate goal is to find biosignatures, definitive evidence of life processes, in the form of particular atmospheric gases, surface features, or even temporal changes in the planet's environment. Each detection or non-detection refines our models and hones the strategies for future explorations, bringing us ever closer to answering the profound question of whether we are alone in the universe. The Drake equation is a probabilistic formula developed by Dr. Frank Drake in 1961, aimed at estimating the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. Although it doesn't provide a definitive answer, it serves as a framework to guide scientific inquiries into the search for intelligent life beyond Earth. The equation breaks down the daunting question into more manageable subcomponents, each representing a variable that can be studied, measured, or estimated through astronomical and biological research. The Drake equation is often written like this: n equals r star times f sub p times n sub e times f sub l times f sub I times f sub c times l. In this equation, n represents the number of civilizations with which humans might communicate. Let's break down the variables. First, r star is the average rate of star formation in our galaxy. This is relatively well understood through astronomical observations, typically estimated to be around 1 to 3 stars per year. Second, f sub p is the fraction of those stars that have planetary systems. Observations from missions like Kepler and TESS have shown that planetary systems are quite common, with estimates suggesting that a significant majority of stars have planets. Third, N sub E represents the average number of planets that could potentially support life per star that has planets. This includes Earth-like planets situated in the habitable zone where conditions might allow for liquid water. Current estimates vary widely, but ongoing research is continuously refining this number. Fourth, F sub L is the fraction of planets where life actually appears. This is one of the more speculative factors, as it is based on our limited understanding of how life originates. Earth is our only data point, making this estimate highly uncertain. Fifth, F sub I pertains to the fraction of life-bearing planets where intelligent life emerges. This also remains speculative because it requires a deep understanding of the evolutionary processes that lead to intelligence. Sixth, F sub C stands for the fraction of civilizations that develop technology capable of sending detectable signals into space. This includes technologies like radio telescopes and other forms of electromagnetic communication. Seventh, L is the length of time these civilizations release detectable signals into space. This could be influenced by a variety of factors, including the longevity of a civilization, technological advancements, or even self-destruction. By multiplying these terms, the Drake equation provides a framework to estimate N, sparking both scientific curiosity and philosophical debates. While the values of the variables are imprecise and highly debated, the equation itself has been instrumental in guiding research programs like SETI, Search for Extraterrestrial Intelligence. It encourages a multidisciplinary approach, integrating astronomy, biology, and even sociology to tackle one of humanity's most profound questions. Are we alone in the universe? Europa, one of Jupiter's moons, is a prime candidate in the search for extraterrestrial life because it is believed to harbor a vast subsurface ocean beneath its icy crust. Scientists have devised several innovative missions and technologies to explore this hidden ocean, aiming to understand its composition, dynamics, and potential for supporting life. NASA's upcoming Europa Clipper mission, set to launch in the early 2020s, is a flagship endeavor in this quest. The spacecraft will conduct detailed reconnaissance of Europa's ice shell and underlying ocean, using a suite of sophisticated instruments. Among these are ice-penetrating radar to map the thickness of the ice and identify subsurface lakes, spectrometers to analyze the surface composition, and magnetometers to detect the salinity and depth of the ocean by studying variations in Europa's magnetic field. High-resolution cameras will capture detailed images of the surface, revealing features like ridges, cracks, and potential plumes of water vapor erupting through the ice from the ocean below. The possibility of water plumes shooting up from Europa's surface, first hinted at by the Hubble Space Telescope, presents an exciting opportunity for direct sampling. If confirmed during the Clipper mission, these plumes could be analyzed by flying the spacecraft through them, allowing for the collection of water vapor and ice particles without the need to drill through the ice. Such samples could contain organic molecules or even microbial life, offering a tantalizing glimpse into the moon's habitability. In the longer term, ambitious proposals for landers and even submersibles are on the drawing board. One such concept is the Europa lander mission, which would aim to touch down on the surface and carry instruments capable of drilling through the ice to reach the ocean below. The lander would be equipped with tools for analyzing the chemical makeup of the ice and any potential organic compounds. More futuristic ideas include cryobots, robotic probes that would melt their way through the ice using heat, and deploy underwater drones, known as hydrobots, to explore the ocean directly. These submersible robots could be outfitted with cameras, lights, and sensors to navigate the dark, high-pressure environment, searching for signs of life and studying the ocean's properties in unprecedented detail. Exploring Europa's ocean requires overcoming significant technical challenges, from dealing with extreme radiation levels emanating from Jupiter to ensuring that spacecraft and probes are sterilized to prevent contamination with Earth life. Despite these challenges, the scientific community is optimistic that these missions will yield groundbreaking insights into one of the most intriguing environments in our solar system. By combining orbital reconnaissance, plume sampling, and eventually subsurface exploration, researchers hope to unlock the secrets of Europa's ocean and potentially discover the first evidence of life beyond Earth. Meteorites have served as invaluable messengers from space, providing a wealth of information about the early solar system, the building blocks of life, and even the potential for life elsewhere. These rocky fragments, which often originate from asteroids and sometimes from other planets and moons, can survive their fiery passage through Earth's atmosphere and land on our planet, where they are meticulously studied by scientists. One of the most significant insights we've gained from meteorites concerns the presence of organic molecules, which are the chemical precursors to life. For instance, the Murchison meteorite, which fell in Australia in 1969, has been found to contain over 90 different amino acids. Notably, some of these amino acids are not commonly found on Earth, indicating that organic chemistry processes occur naturally in space. This discovery supports the hypothesis that the early building blocks of life may have been delivered to Earth via meteorite impacts, possibly kickstarting the development of life. Meteorites also provide clues about the primordial conditions of the solar system. The analysis of isotopic ratios within these rocks, ratios of elements like hydrogen and carbon, helps scientists understand the processes that shaped the early solar system's matter. For example, chondrites, a class of stony meteorites, contain tiny spherical inclusions called chondrules, which offer insights into the conditions and processes of the solar nebula from which our solar system formed. Particularly intriguing are the Martian meteorites, like ALH 84001, which was found in Antarctica in 1984. This meteorite is believed to have been ejected from the surface of Mars by an asteroid impact and traveled through space before landing on Earth. Inside ALH 84001, scientists discovered tiny carbonate globules that some researchers initially interpreted as fossilized evidence of Martian microbial life. Although this interpretation remains controversial, the meteorite nonetheless revealed the past presence of liquid water on Mars and sparked significant interest in Mars as a habitable environment. Isotopic analysis of meteorites also helps discern the history of water in our solar system. For example, some meteorites contain minerals that suggest they once had water locked inside them. By studying these hydrated minerals, scientists gain insights into the distribution and history of water in the early solar system. This has implications not only for understanding Earth's water sources, but also for assessing the habitability of other celestial bodies. Meteorites have greatly enriched our understanding of life's potential in space and the early history of the solar system. They have revealed the presence of organic molecules and provided evidence of the chemical processes that could lead to life. They also offer clues about the history of water in space and the possible past habitability of planets like Mars. Through these extraterrestrial rocks, we continue to piece together the puzzle of life's origins and distribution in the cosmos. Studying the potential for life on Mars is a comprehensive and multidisciplinary effort that involves a combination of robotic missions, remote sensing technology, and Earth-based laboratory research. Scientists focus on understanding Mars' past and present environment, searching for signs of water, organic molecules, and other conditions conducive to life. Robotic missions have been at the forefront of this investigation. NASA's Mars rovers, such as Spirit, Opportunity, Curiosity, and the recently landed Perseverance, are equipped with an array of sophisticated instruments designed to explore the Martian surface. Spirit and Opportunity revealed evidence of ancient water flows through the discovery of minerals and geological formations that form in the presence of water. Curiosity, which landed in Gale Crater in 2012, has analyzed rock samples and found organic molecules, complex carbon-based compounds that are essential to life. It also discovered evidence that Gale Crater once hosted a lake with conditions that could have been habitable for microbial life. Perseverance is taking this search to the next level. Equipped with advanced scientific tools, including the Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, and PXL, planetary instrument for X-ray lithochemistry instruments, Perseverance is searching for biosignatures and drilling core samples of Martian rocks. These samples are being cached for a future mission to return to Earth, where they can be analyzed in state-of-the-art laboratories, potentially providing definitive evidence of past life. Remote sensing technology also plays a crucial role. Orbiters such as NASA's Mars Reconnaissance Orbiter, MRO, and the European Space Agency's Mars Express use high-resolution cameras and spectrometers to analyze the planet's surface and atmosphere from above. These orbiters can identify mineral deposits, map ice distributions, and even detect subsurface water through radar. Observations from these spacecraft help scientists identify promising landing sites for future missions and provide a broader context for the findings of surface rovers. Mars' seasonal methane emissions offer another intriguing line of investigation. Methane can be produced by geological processes, but on Earth, a significant amount of methane is produced biologically. The periodic detection of methane in Mars's atmosphere, as observed by both instruments on the Curiosity rover and the Trace Gas Orbiter, raises the exciting possibility that microbial life could exist on Mars today, although non-biological explanations remain possible and are actively studied. Laboratory research on Earth complements these efforts. Scientists study Mars' analog environments, places on Earth that mimic Martian conditions, such as the Atacama Desert in Chile or the dry valleys of Antarctica. These studies help researchers understand how life can persist in extreme conditions and develop techniques for detecting life that can be applied on Mars. Researchers also perform experiments that simulate Martian environmental conditions to test the survival and adaptability of microorganisms. The search for life on Mars is a multifaceted endeavor that integrates robotic explorers, orbiters, laboratory simulations, and multidisciplinary scientific research. By compiling data from surface missions, orbital observations, and Earth-based studies, scientists are piecing together the history of Mars' climate and geology, searching for chemical evidence of life, and laying the groundwork for future human exploration that may finally answer whether life ever existed on the Red Planet. The discovery of phosphine on Venus has stirred significant excitement and debate within the scientific community, as it suggests the potential for life or unknown geochemical processes in its atmosphere. Phosphine, pH3, is a molecule composed of one phosphorus atom and 3 hydrogen atoms. On Earth, phosphine is produced by industrial processes or by anaerobic, oxygen-free ecosystems, including microbial activity. Its detection on Venus is intriguing because it raises questions about the potential for biological or chemical processes occurring there that are not yet understood. The discovery was made using observations from the James Clerk Maxwell Telescope, JCMT, in Hawaii, and confirmed by the Atacama Large Millimeter-Submillimeter Array, ALMA, in Chile. These instruments detected a spectral signature consistent with phosphine in the clouds of Venus, where temperatures are relatively moderate compared to the searing surface below. The concentrations detected were much higher than could be accounted for by known abiotic processes, such as volcanic activity, lightning, or reactions involving sunlight and minerals. The significance of this finding lies primarily in the context of astrobiology and planetary science. Phosphine is a potential biosignature gas because on Earth, its production is largely associated with life processes. If the phosphine on Venus is indeed biogenic, it could imply that microbial life exists in the temperate but highly acidic clouds of the planet, challenging our understanding of where life can thrive. However, it is crucial to exercise caution. The detection of phosphine does not necessarily mean life exists on Venus. There are many unknowns and complexities regarding Venusian chemistry. The discovery has prompted scientists to propose alternative, non-biological mechanisms that might explain the presence of phosphine. For instance, there could be exotic chemical reactions happening under the extreme conditions in the Venusian atmosphere that we do not yet understand. To build upon this discovery, further observations and missions are essential. Upcoming missions like NASA's Veritas, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, and ESA's Envision aim to provide more detailed analyses of Venus's atmosphere and geological features. These missions could help discern whether the detected phosphine is a byproduct of unknown abiotic processes or a potential indicator of life. The discovery of phosphine on Venus is significant because it opens new avenues for research into both planetary science and the search for extraterrestrial life. It challenges our current understanding of atmospheric chemistry and underscores the need for further exploration of Venus's atmosphere to determine the true nature of this enigmatic molecule. The findings have reignited interest in Venus, often overshadowed by Mars, as a candidate in the quest to answer one of humanity's most profound questions: are we alone in the universe? When scientists classify exoplanets in terms of habitability, they often focus on a variety of factors that determine whether these distant worlds could potentially support life. First and foremost is the concept of the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where the temperature is just right, not too hot and not too cold, for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it. For instance, a planet that's located too close to its star might experience extreme temperatures that would boil any surface water away, while one too far might be so cold that water would remain perpetually frozen. Beyond the habitable zone, scientists also look at factors like the planet's atmosphere, size, and composition. A thick atmosphere rich in greenhouse gases such as carbon dioxide can trap heat and maintain liquid water, even if the planet is on the colder edge of the habitable zone. Conversely, an atmosphere that's too thin might not be able to support stable surface conditions. The planet's size is also crucial. Those that are too small may not have sufficient gravitational pull to hold onto an atmosphere, while those that are too large could become gas giants with hostile environments. Additionally, the presence of elements such as oxygen and nitrogen in the atmosphere could indicate chemical processes that are potentially conducive to life. With advancements in technology, including space telescopes and spectrometers, scientists continue to refine these criteria, making the exciting search for habitable exoplanets more precise and hopeful.